Hello, my name is Michelle Alcala. I'm from Brownsville, Texas, and a rising senior in LFHS. In the future, I plan to pursue aerospace engineering and astrophysics.
Hi, my name is Angel Hu, and I'm a rising junior at Central Magnet School in Murfreesboro, Tennessee, and I would like to pursue a career in physics or astronomy.
Hello, my name is Gowri Nanda, and I am from Frisco, Texas. I'm currently a rising senior at the Texas Academy of Mathematics and Science, and I aspire to study computer science and astrophysics in college.
Together, we are in the group Galaxy Classification and the subgroup Dark Energy Explorers. For our project, we separated nearby and distant galaxies using HETDEX citizen science data. For our outline, we'll be discussing the context of this entire project and the process in which we collected our data. The universe is expanding, we know that already, but upon a second shock starting in the late 1990s, when two teams gathered distances to high redshift supernovae, presented their data, we have learned that that expansion is actually speeding up.
As the universe expands, light from distant galaxies is stretched to longer wavelength, and this equation for redshift is essentially just the change in wavelength, where high energy light waves move down the electromagnetic spectrum to infrared light and takes a more red tone. Edwin Hubble explored redshift to identify the velocity of galaxies, and he deduced that they were moving away from the Milky Way. He came up with Hubble's constant, suggesting that the universe expands at the same rate in every location. However, Hubble's constant deviates from a linear relationship at high redshifts, and redshift and distance do not have the same relationship as previous models predicted. Using numbers from the Ned-Wright cosmological calculator, we plotted two lines, one accounting for the mass density of dark energy and one ignoring the effects of dark energy. This produces a relationship that deviates at redshifts greater than 0.5. Thus, at higher redshifts, Hubble's constant does not hold true and the universe does not expand at a constant rate, possibly as a result of dark energy.
What is the cause of this? Astrophysicists took the term of this phenomenon to be dark energy, which is thought to be the acceleration of expansion when introduced by American cosmologist Michael Turner in 1998. The name has no correlation to what is involved, and the nature of this subject is still debatable. Whether dark energy is a cosmological constant or something that causes galaxies to be pushed away, we do not exactly know what it is yet. When exploring dark energy, we absolutely have to bring up dark matter and not get them confused. Dark energy is not the same as dark matter, but they both serve roles regarding the fates of the model of the universe. Dark matter makes up most of the mass of the galaxies and galaxy clusters, and it keeps them gravitationally bound together in a structure. They are assumed to be a mixture of dust and remnants of stars, planets, basically matter that does not emit light that is visible or infrared. Dark matter is probably a yet undiscovered particle, which does not emit any EM radiation. In the 1930s, dark matter was introduced by Fritz Zwicky through his calculations for the Coma cluster. These calculations contained errors that gave proof to the existence of dark matter. The reason being is that the cosmic cluster was rotating at such a speed that it could not hold its own structure. Therefore, there must have been matter that is not seen by the eye keeping it together. So the most exciting part of science is realizing we might have misunderstood absolutely everything, including the fundamentals. Should dark energy and dark matter actually exist, our interpreted composition of the universe is backwards, leaving observable luminous matter to be only 5%.
Thus, to contribute to the search and study of dark energy in the universe, we turn to classifying galaxies from the HETDEX Citizen Science Project. HETDEX, also known as the Hobby-Eberly Telescope Dark Energy Experiment, is a currently ongoing project at the University of Texas at Austin's McDonald Observatory that takes spectrograph images of many galaxies in the universe. The way this project works is that it is able to collect data during clear nights in the sky, and also the main goal is to get the redshift, or eventually get the redshift of distant galaxies in order to create a 3D map of the universe to study how dark energy is able to cause the acceleration of the expansion of our universe. VIRUS, also known as the Visible Integral Field Replicable Unit spectrographs, is a tool that takes 150 specters of the sky to create different images in different wavelengths. This is done to detect for different objects that might be detected in the sky. This tool is made to collect data from galaxies that are 9 to 11 billion light years away in order to create the final map and study the universe in a deeper way. So where does citizen science come in? So HETDEX needs to pick up only the distant galaxies from this huge set of observations. Instead of solely relying on scientists to just look at thousands of images from HETDEX, citizen science is able to allow normal citizens like you and me, just regular people, to contribute to such a big project by helping classify this data. While we can use artificial intelligence has many limitations. Humans are much better at differentiating and checking between what is a galaxy, what is not a galaxy, and being able to differentiate between a distant and a nearby galaxy. However, in order for the artificial intelligence algorithms to work, machine learning is required, and in order for machine learning to work, we need human input and human data to be able to make sure that that works correctly. So therefore, the Zooniverse Dark Energy Explorers project is a project that allows citizens to provide data for the machine learning, and this allows us to speed up the research on this project. And while it also allows citizens to participate in a STEM project and participate in research like this, it also educates the public on STEM, which is very exciting because this can foster and inspire many people to be excited about topics in STEM and potentially even pursue this kind of research in the future. So here's how we analyze the data. So what we wanted to do is we first wanted to look at different images and be able to figure out if it's a galaxy or not, or if it is nearby or far away. So first, as you can see, all of the spectra that we get from HETDEX comes in images that we have to process. As you can see in the throwback, you can see that in each of the colored boxes, which represents the area of focus in a different wavelength, you can see that there are no strong dots. So if you can see a black dot, that indicates that a photon of light is being detected. However, you do not see many black dots or clear black spots in the throwback image. So that means that this is clearly just noise. Additionally, we can also see that the curve does not fit very well. There are many outliers in the graph itself, and there's also no signature. If you can see a yellow dot in the signature, then that can indicate that there is an object being detected. However, we are unable to detect anything from that area. As well as in the main area of focus, we can see that around that area of focus, there are other objects as well. And so the area of the main focus in the red box does not really have anything that we can actually detect anything from. However, from the keep section, we can see that a dot appears in the focused areas in several different wavelengths, and the curve fits very well. Additionally, there is a very, very small and faint area for the object of focus to be focused on. And there's also a yellow dot that indicates that there is some kind of signature that is being detected. We can tell that the keep is a distant galaxy. Meanwhile, what we have to throw back is noise, which will not aid us in our research. So when we are analyzing the data, we need to check for clear points in all of the colored boxes, which will indicate that it is a galaxy. We also need to make sure that the spectral points, the blue dots with the error bars, are fitting with the curve. If it's a good fit, then it might be a galaxy or maybe another object. And if it's a bad fit, then it's noise that we don't really need. Therefore, human input is very necessary for precision and accuracy of making sure that all of this data is being processed correctly.
So what can the fit and the shape of the spectral lines tell us? Well, they can tell us the type of object, as black holes typically have flatter peaks and stars and galaxies usually have longer spectral lines. They can also tell us about the composition. The wavelength of spectral lines in the full spectrum, which the database does not provide, can tell us what elements are present in the object. Redshift. Calculating the difference between the redshifted wavelength and the rest wavelength and dividing it by the rest wavelength gives the value for a redshift. Thus, the higher the redshift, the further the objects. And the database does not provide this data since we are picking galaxies for which redshift needs to be measured. And finally, nearby objects. Nearby objects caught in the image can affect the spectra, and phenomena such as galaxy mergers or collisions, star formations, supernovae, and black hole accretions often generate spectra with many peaks and valleys which may not appear to fit on the line. Part of the project is to separate nearby galaxies from distant galaxies. Nearby galaxies usually have a distinct shape in the signal, a clear black dot, and spectral lines with a very close fit. Distant galaxies, on the other hand, usually have fainter signals, which make the data points noisier and more scattered around the black line, appearing to be not as close of a fit. We can also classify different galaxies by using the images and the signals and the spectral lines. For example, spiral galaxies have distinct spiral arms in the image and very strong emission lines with a very high peak and a very close fit with a clear signal. Elliptical galaxies, on the other hand, are usually farther away with not as clean of a fit and many smaller peaks in the lines. Irregular galaxies are somewhere in between and do not have a distinct shape, but like the spiral, have very short lines and a high emission peak.
Other objects that we classified from HETDEX data include things like black holes. So as you can see, black holes are very strong, and you can see a very long dark streak appearing through different frequencies as well. And so this first image indicates that this is a black hole in a galaxy. You can also see that in the area of focus, you can definitely see that there's some kind of shape that indicates that the object that it is focusing on is a galaxy as well. The second image contains an asteroid. In the big image that you can see that there's a very long line going through the image. That indicates that there's an asteroid. An asteroid can provide some noise, so that is definitely something that we have to check for. However, in this image, we can also see that the asteroid is just a long dark streak in the full image, which is very cool. Finally, another type of image that we can see is a star. If you can see a lens flare kind of image appearing, that indicates that there's a star that is being detected as well, and also being shown in the images. While these cases are not distant galaxies or exactly galaxies, it is still very interesting to be able to tell and differentiate between different objects in space.
Now that we have gathered our data, we can now present our statistics with different focus. Our first set of statistics discusses whether our data was real or fake. And the total of 317 classifications we accumulated together, about 177 were real signals, and 140 were just noise, fake signals from the telescope, instruments, stuff like that. For our second set of statistics, we discuss if galaxies are nearby or distant. Our distant galaxies accumulated were 75, nearby was 73, noise was 139, and a new category of other being black holes, stars, and asteroids being flat 30. If you would notice here, noise once was 140, however now it is 139, specifically for these set of statistics. That being due to one of our data points fitting in the new category labeled other. Though it is still noise, it suits this category much better. And for our last set of statistics, we discussed the type of celestial objects that we viewed within these data sets. Of course, 148 were galaxies, our main area of interest. However, 24 were black holes. We found 5 stars and 1 asteroid.
Some of the potential personal challenges and also future issues with the Dark Energies Explorers. Some of the challenges and potential issues with the Dark Energy Explorers project includes a large amount of data, as not every observation is useful. As you can see with the statistics, there was a lot of noise and a lot of other objects that may not be able to help with us calculating the redshift. Additionally, there's no automated algorithm, which does require a lot of user observations to be able to complete. And for our own project and our own calculations, there was no right ascension and declination. Due to this being a citizen science project, we were not really able to access a lot of the specific details of many of the subjects and many of the galaxies that we classified. So finding the right ascension and the declination, or the coordinates of the stars, would have helped us to be able to actually find the redshift and make calculations. However, since those were not provided, we were unable to make many calculations.
So how will researchers at HETDEX use this information to gain more insight about dark energy? There are some calculations that can be made using the redshifts of distant galaxies. We could calculate their distances away from us and each other to create a map of the early universe. We can use baryonic acoustic oscillations to analyze the distribution of distant galaxies, which can tell us about the effect of dark energy on the early universe and provide insight to how the universe expanded and accelerated in the beginning.
So how can this help us in the search for dark energy? By aiding the process of clarifying data in the HETDEX project, we're able to proceed further in science, as scientists can now focus on creating an accurate model of the universe with precise measurements. Essentially, we are the first step. We're the first step to solidifying distance of distant galaxies and their ages. In the end, this will let us know if dark energy is truly out there or if we have fully misunderstood gravity itself.
On all of us, SEAS has had a very big impact, from allowing us to learn about different topics in the space field, as well as letting us network with many mentors and many individuals in the industry, and as well as inspiring us to continue pursuing this topic. SEAS has definitely inspired us and has impacted our lives in many ways. And also, it was just a lot of fun.
For me, SEAS has allowed me to delve a lot deeper in the fields of astronomy and physics, and I am much more inspired to pursue a career or study those fields in college now. Additionally, I have had the opportunity to make many great friends and meet many like-minded individuals who have inspired me to keep on going with my research and not give up.
As someone who's interested mainly in aerospace engineering, I'd always focus on the mechanics and just building the rocket, building the satellite. But after working on projects such as these and being with other people who are like-minded, I've gained a new interest in astronomy, and I hope to use my aerospace engineering skills to, proceed in the science of astronomy, like making a telescope in that sense.
Personally, SEAS has impacted me a lot by allowing me to network and get to meet a lot of people in the industry as well. It was just so much fun to get to work with my mentor, and I also really loved getting to talk with a lot of NASA scientists and also with the speakers that have come during our internship. Definitely, I love astronomy and physics. However, it was just so much fun to actually get to work on a project involving those topics and even look into future applications for fields that I want to study, such as computer science and programming and other things in astrophysics as well. Definitely, this project was a lot of fun, and I'm very glad that I got to participate in SEAS. With all of that being said, we'd love to thank this program. We'd like to thank NASA and the Texas Space Grant Consortium, TSGC, for funding the SEAS program, and the Center of Space Research at the University of Texas at Austin for letting us use their facilities. We'd also love to thank Mrs. Selena Miller and Mrs. Margaret Baggio and all of the chaperones and people who have helped contribute to this program. We greatly appreciate your support and help in this project. Additionally, we would like to thank our wonderful mentor, Dr. Judit Ries, for guiding our project and giving us a lot of support in this field. We appreciate her very much. And a special thanks to Dr. Carl Gebhardt. Dr. Carl Gebhardt actually created the Dark Energies Explorers Citizen Science Survey, and he also presented to us about dark energy and black holes. Definitely check out the Dark Energy Explorers project on Zooniverse, and you can also classify galaxies yourself to contribute to this research project. With that being said, thank you very much for listening to our presentation. If you have any questions, please let us know. Thank you.